Hello friends, I welcome you in lecture number 18 on complex functions. In this lecture we will discuss one more question which was asked in GTU Winter 2019 examination. So the question is about to check the points at which this function is analytic. So we have to determine whether this function is analytic at any point or not. So for that we recall the definition of analytic function. We know that a function f of z is analytic at some point z0 if there exists at least one neighborhood of z0 such that this function is differentiable at every point in that neighborhood. So to decide analyticity, first we have to determine the points at which function is differentiable. And to decide the differentiability, we are using Cauchy-Riemann equations. So we know that Cauchy-Riemann equations are del u by del x equal to del v by del y and del u by del y equal to minus del v by del x. So if these Cauchy-Riemann equations are satisfied at some point z0 and if these first order partial derivatives are continuous at z0, then function is differentiable at that point z0. So first we decide the number of points at which this function is differentiable, and then using the definition of analytic function we will be able to decide the points at which function is analytic. So first we write the given function, which is 3x plus y plus I times 3y minus x, and if we compare with u plus iv, we have u equal to 3x plus y and v equal to coefficient of I, which is 3y minus x. So first we find out partial derivatives of u and v. So therefore if we differentiate u with respect to x, we consider y as constant, so derivative of y is 0, derivative of 3x is 3 with respect to x. Similarly del u by del y, so for that we consider x as constant, so derivative of 3x is 0, derivative of y is 1. Similarly del v by del x will be derivative of 3y is 0 minus 1, which is minus 1, del v by del y is derivative of 3y is 3 and derivative of x is 0, so it is 3. So if we check first equation, that is ux equal to vy, then we can see that del u by del x and del v by del y are equal at each point, because del u by del x at any point is 3 and del v by del y at any point is also 3. So this equation is satisfied at any point z in the complex plane, at any point z equal to xy. Second Cauchy-Riemann equation is del u by del y equal to minus del v by del x. So here del u by del y is 1 at any point, del v by del x is minus 1 at any point, so if we take negative of del v by del x we will have 1. So second equation is also satisfied at any point, del u by del y at any point xy is 1, which is equal to negative of del v by del x at any point xy. So this is also satisfied at any point z equal to xy in the complex plane. So we can see that therefore Cauchy-Riemann equations, both equations are satisfied at every point. Cauchy-Riemann equations are satisfied at each point in the complex plane, at each point z equal to xy in the complex plane, or we can simply write plane also, in the complex plane. And if we observe these partial derivatives, all partial derivatives are continuous because they are constant functions. So we have to check second condition also. So it is clear that all the partial derivatives of first order of u and v are continuous. So we can write that these are continuous because they are constant functions at each point in the complex plane. Z equal to xy in the complex plane. So both the conditions for differentiability are satisfied, Cauchy-Riemann equations are satisfied, and these partial derivatives are continuous. So therefore we can say that given function is differentiable at each point in the complex plane. Given function is differentiable at each point in the complex plane. And now we have to decide the points at which function is analytic. So for analytic function, suppose we want to decide analyticity at this point, then function is analytic at this point if function is differentiable in some neighborhood of this point. Now this function is differentiable at each point in the complex plane. So if I take any neighborhood of this point, function is going to be differentiable at every point in this neighborhood, and this will be true for every point because our function is differentiable at every point. Therefore function is differentiable in every neighborhood of every point. So this means function is analytic at any point. Therefore f of z is analytic at each point in the complex plane. Or we can say that f of z is analytic everywhere, analytic at each point in the complex plane. And the same statement can be written as, in other words, f of z is analytic everywhere, and the function which is analytic everywhere is known as entire function. So this function is entire function. So it is easy to decide the analyticity of a function. First we have to determine the differentiability. For that we have to decide at which points Cauchy-Riemann equations are satisfied. Then at those points we have to check continuity of partial derivatives, and once we know that function is differentiable at this number of points, we can use the definition of analytic function. Or we can remember that if function is differentiable everywhere, then we can directly write that function is analytic everywhere, because if function is differentiable everywhere, then it is going to be differentiable in every neighborhood of every point. So if function is differentiable everywhere, we can directly write that function is analytic everywhere. And similarly, if function is nowhere differentiable, then we can write that function is nowhere analytic. The function which is not differentiable at any point is also not analytic at any point. So everywhere differentiable implies everywhere analytic, nowhere differentiable implies nowhere analytic. Okay, so this is all about this session. I hope you like it. Thank you very much.